Everyone here understand?
Yes.
Okay, now let's apply this to mathematics.
My hand hurts.
Okay.
Julio, you want to take over? If, for now, let's just say, let's make it simpler, Fermat's little rule. And I'm just going to say, if P does not divide, actually, instead of P does not divide, let's just say, just consider, because we're working modulo P. Consider if A is in the set 1, 2, up to P minus 1. Actually, you know what's better to say if P does not divide. Then, A to the P minus 1 is identically 1 mod P. It's beautiful. We saw beautiful application this morning. 341 divides 6 to the 22 minus 2, right? Oh, how do you know that? It's beautiful. Thank you very much. Okay, also application, the extension of that is Euler's theorem, and it can be applied to the RSA. Okay, so proof. Okay. Consider a function phi of x. So f of x equals kx. Consider this function, okay? I claim, okay, so I have an arbitrary name, I have an a, right? I claim few things about f of x equals a. Everyone here knows what a function is? Does everyone know who does? Raise your hand if you know what a function is. Woo! All a function is you give me something, and I do something with it. I can take it, and I can multiply it by 2, I can minus 5, I can square it, I can take it, I can put it in the trash can and hide it. Things like that. You give me something, I tell you. So first thing you notice, two properties. One, first property. Notice that, okay, let's just consider, let's just put these. Let's just have A in the set 1, 2, up to 1. It's a working mod P. It really doesn't matter. And I just realized why I wanted that. Okay, so my question is, when you take this mod P, is this guy, can this guy equal 0? My question is, can this equal 0? So, okay, by the way, F takes the space of 1, 2, P minus 1, and now I claim that it maps to the same set. You guys understand what I'm saying? So when you have a function, I can tell you what can be passed through it. I can say the real numbers. I can say you can accept arguments as complex numbers, or maybe just integers. Here I say only 1, 2, up to P minus 1. My question is, when I multiply by A, is it possible when you take mod P, it equals 0? The answer is no, because remember, proof by computation. Suppose AX was identically 0. But here's something to learn when you do mod P. Good question, guys. Is A relatively prime to P? What's the greatest common divisor between A and P? 1.
What?
You set it up there, but we haven't used it in this one.
Because A is in the set 1, 2, up to P minus 1. So it's relatively prime, right?
Yeah.
So so that means we have an inverse, right? How do I know there's an inverse to A?
Because
my lemma says that there's an inverse to A. We have an x such that AX identically 1, right? There's some value that can multiply by A to make it 1, right? Okay. It would be better if I just write A inverse equals x. So I multiply both sides by A inverse. Right? What's A inverse times A?
1.
It becomes, what does it become?
1.
Good.
since this says x is identical to 0, mod p, is it possible from these possible values that they equal 0? Why? Because it's only 1, 2 up to p minus 1. So that's the first thing I know. They only match to this set. Second, I know, can I map two things to the same object that are different? No. Okay, suppose I could. So let's look at AX. Suppose AX equals AY. Suppose I have a monkey map, some waffle map to the same place as squirrel. Okay? Suppose that was true. Okay? What can I multiply both sides to get rid of? What inverse?
1 over A.
Mr. Cody? Okay, multiply both sides by?
1 over A.
I can multiply both sides by A inverse, which is guaranteed by the lemma. So this says x equal y. Or suppose AX is identical to AY. Then it says mod p. Then it says x identically y mod p. But I assume x is not identically y. Oh, oops. So we have a contradiction. So this says every animal has to go to different cage. Right? But here's the thing. I've got to bring this up because I forgot that we have only 5 many cages. If I have p animals going to p different cages, then is it possible, and they all go to distinct cages, is all the cages filled? Yes or no?
Yes.
All filled. So we just have a reordering of animals, right? Everyone agree?
Yes.
Why do we have this reordering of animals? Because each animal goes into their own cage, and we have p animals, and therefore there must be p cages. And I know it maps with p different cages. Is good? Okay. So look at A times 1 times, okay, look at F1 times F2 times F3 times Fp minus 1. What does this equal to? It equals to A, it equals to A times 1 times A times 2 times A times 3 up to A times C minus 1. Right, guys? Okay. So then from here, but here's the thing, as I just proved before, it was just a reordering, right? Right? There was a bijection, right? I proved it to you guys.
Yes.
So we also know this guy equals, it's a reordering of animals. And each one gets their own cages. What is the image of this guy? What is the possible animals this guy shape? Either 1, 2 up to p minus 1, right? And it was just a reordering of animals. So it's equal to 1 times 2 times 3 up to p minus 1, right guys?
Yes.
Okay, why is it reordering of animals? Can someone explain to me? Because we know that this space under this function maps again to this space. I proved it. Does not map to 0 when you do mod p. And therefore, and we also know that it's a bijection, as I argued.